So now we are going to look into what are called as antennas. Antennas are to be treated like the eyes or the ears of a communication system. So we saw earlier that when you have a typical communication system, there is going to be a transmitter. The transmitter is typically connected to an antenna. Then the antenna would radiate the RF energy in a wireless medium, which is air, which is wireless. There is a receive antenna that picks up the received signal, and then that gets processed by the receiver. So in that sense, this element over here is what we call as an antenna, which is like the ear or the eyes of the communication system. So in essence, what it does is there is going to be a certain generator that generates the transmitted signal that is carried by a transmission line in a wired medium, and what essentially the antenna does is a transducer that converts this energy in the wired medium to wireless in an efficient way. It does that in an efficient way, and once this energy propagates through the wireless channel, the antenna then is also able to convert back from wireless to wired energy that flows through a guided transmission line and reaches a receiver. So you see there are two kinds of propagation here. One is the guided, which is through the transmission line, and the unguided, which is through the open space, the free space over here. So an antenna is a transducer that converts guided to unguided, and the reciprocal as well, the vice versa as well, that converts unguided energy back to guided energy. So that property of an antenna is called as a reciprocity, which means that this so-called passive antenna, all passive antennas have this property. Passive meaning they are not powered. They have this property of reciprocity where the same antenna can be used for transmitting as well as receiving an RF signal. So this scenario that you see here for a typical TX-RX chain, this animation nicely captures how the propagation happens from a guided phenomenon. In this case, it's a waveguide. It's essentially a waveguide that is being converted into unguided transmission here in free space through an antenna which we call as a horn antenna. This antenna is a horn antenna. So this is the transmitter and this is the receiver, where the receiver antenna picks up the wireless signal and converts it back to guided energy, delivering it to the receiver which will be connected as a load to this antenna. So this horn antenna is one of the kinds. There are various other different kinds of antennas. We see that wire antennas typically that you can see on rooftops of buildings for TV reception, also in cars for FM radio, so on and so forth. The second category is the aperture antennas. Aperture meaning some kind of an area, like what you see here is a horn antenna. It has a so-called rectangular aperture, like what you see in this animation here. There are microstrip antennas that are built on printed circuit boards, where you have a certain copper patch and a dielectric material in between, and then on top is the copper. On top of it is the copper, which is the metal that carries the charges. Whenever the charge is accelerating or decelerating, that's when the antenna is radiating an electromagnetic energy. So the fourth category is reflector antennas that you see here, typically used for satellite TV reception, the third category, the fifth type is the lens antennas that you see where the aperture is essentially an aperture antenna with the aperture being filled up with a lens, so that the radiation characteristics are more controlled in that sense, having some advantages over aperture antenna. The most popular these days are the chip antennas for all the small electronic modules, where the antenna is made of a very high dielectric material, The dielectric constant epsilon, if it's too high, then for a given frequency the wavelength will get lower, then the physical size of the antenna can also get lower. The physical size is typically proportional to the wavelength, the radiation wavelength of that particular antenna. And since the dielectric constant is too high, the lambda is very low, the size of the chip antenna can be very low and can be integrated along with the radio modules that you see here. And the last category is an array antenna, where you're having the same individual antenna element that is being repeated so that they have certain characteristics, so that the effective radiating aperture is much bigger than the individual antenna elements. Here you see it's a square antenna, 4x4. Any kind of these 6 different antennas can be placed as an array. Like what you see here is a radio telescope where an aperture antenna is being used but physically separated in space, and because of that these antennas have typically very large gains rather than a single antenna alone. Array antennas typically have a very large gain, so we will see what gain is later on. So gain is one parameter of an antenna, but we are going to look into the other parameters, the parameters that describe the performance of an antenna. So what we see earlier is that when we have a guided transmission line with a characteristic impedance Z0, the antenna is a transducer that converts the guided transmission into wireless transmission unguided. So this antenna becomes the load for this transmission line. So equivalently, the entire antenna can be represented by an equivalent impedance, antenna impedance, what we call as the antenna impedance, which has a real part and imaginary part like any other impedance. So the real part essentially captures how the antenna radiates out energy. As you see, this is a load. This load might have a lossy load where energy is lost. Then the resistance is going to be a high value, and what this resistance really signifies is the radiation mechanism that is captured as loss. The radiation captured as loss by this resistance. We know when there's a resistance, there's I square R ohmic loss. That kind of loss is being captured as the radiation, equivalent radiation that the antenna does. The imaginary part of the antenna does not really lead to radiation, but it is the stored energy. It leads to stored energy, where the energy doesn't really leak out, but instead it is in the vicinity of the antenna. It is being stored in the vicinity but not effectively radiating. So for an antenna, we would want the radiation to be maximum, but the stored energy should be minimum. That means the imaginary part should be 0. The radiated energy must be high. That means the radiation must be matched to the feeding transmission line. So when we go into the match, we can go back and describe that this antenna is having a certain load which is connected to a transmission line. I can always define the reflection coefficient at the load terminal as this being the load impedance and Z0 being the characteristic impedance of the transmission line that is feeding it. So the ZL minus Z0 over ZL plus Z0, that applies here. So the antenna's impedance will be able, from that we can be able to get the reflection coefficient of the antenna. And in general, this is a complex number because the antenna impedance in general can be a complex number, while Z0 is typically 50 ohms. So given a reflection coefficient, we can make this guy to be the subject. We can always rearrange the terms and find the antenna impedance for a given reflection coefficient of an antenna. That can be worked out as well. So if we go ahead and rearrange this expression here, we can get the expression for the antenna that way, as shown here as Z0 into 1 plus gamma over 1 minus gamma, where Z0 is the characteristic impedance. So we can go on and define, just like how we define for a transmission line with a load, we can define what is called as a VSWR. So rather than specifying the reflection coefficient for antenna, some specifications, some data sheets might have what is called as the standing wave ratio of the antenna, which, like what we saw much earlier, is the same as 1 plus modulus of gamma over 1 minus modulus of gamma. So what it physically means, the standing wave ratio, is what we are trying to see here. Is there is a transmission line with certain characteristic impedance Z0. Let's say it's terminated with a load impedance which is not equal to Z0. Instead, it is 3 times Z0. Let's say, for example, it's 3 times Z0. You can clearly see that there is a mismatch, and because of this mismatch, there is going to be a certain standing wave on the transmission line itself because of this mismatch, and we are looking at a particular frequency for which the wavelength in the transmission line is equal to one wavelength. The physical length of the transmission line is equal to one wavelength at that particular frequency. If you were to look at the signal at that particular frequency, how the voltage is distributed across the transmission line, we would see that this is going to be a standing wave with having a certain V max and a certain V min, a voltage minimum and a voltage maximum. The ratio of the voltage maximum over voltage minimum is what we call as the standing wave ratio. So just like how for other arbitrary loads we used to define what is called as the return loss, what is the reflection based on the return loss, which is minus 10 log 10 of gamma A square. What is the return loss of the antenna? That depends on the reflection coefficient. How much is the reflection coefficient? So typically this reflection coefficient, the magnitude of the reflection coefficient is going to be between 0 and 1, which means the return loss is going to be somewhere from infinite to all the way to 0 dB. Return loss in dB is going to be infinite to, so 0 return loss means it's a perfect match, and 0 dB return loss means it's a perfect mismatch. So we would want to achieve a return loss of infinite dB. That means the reflection coefficient gamma A must be as low as possible. If the gamma A is 0, then we see that the VSWR will be equal to 0. So if gamma A is equal to 0, which means a perfect match, then the VSWR is equal to 1, meaning the voltage min and the max, they will be the same value over here. So we can look at the impedance of the antenna like what we see here. It is having RA plus JXA. We can look at that, and turns out that for all antennas this is a function of frequency. That means the resistance is a function of frequency and the reactance is a function of frequency. So if we were to plot it as a function of frequency, we will see that, let's say the blue curve here is the resistance. This is the resistance curve, how it depends upon frequency, and the red curve is the one what we see is the imaginary part, which is denoted by the red curve here. So we see that the frequency, as we sweep from minus 1.8 to 3.2 gigahertz for this example, we see that the imaginary part is equal to 0 at a certain frequency, and that we call as the resonant frequency of the antenna. So that's when the reactance is 0 and the antenna is having a resistance alone, and it is having a nice little resistance alone at that frequency. The imaginary part is 0. Though that resistance is not exactly 50 ohms, but in this particular case that resistance is some value, maybe somewhere around 77 ohms or something, but here the imaginary part is 0, so that becomes the resonant frequency of the antenna. So we can see the frequency response of the antenna in terms of the real part and imaginary part. We are plotting two curves. Another arbitrary way of looking at the same information conveyed in a different sense is to look at the so-called reflection coefficient directly. To look at gamma A square, 10 log 10 of gamma A square. This becomes the reflection coefficient in dB. If we were to plot this, of course gamma is going to have both real part and imaginary part, or it's going to be a complex number, but we are only interested in the magnitude of it to see how much is the match and mismatch. Turns out that it is going to be frequency dependent as well, and we see that higher the value, it is a mismatch, and higher the value, it is going to be a mismatch, and there is a certain frequency band where the value is lower than the minus 10 dB point. That is what is the band in which the antenna can be effectively used. So lower the reflection coefficient, the better the matches. That means the antenna is accepting the power and radiating it, and this minus 10 dB is a good gauge. Minus 10 dB point is a good gauge in terms of the how much is the reflection back that is being accepted by the antenna, how much power is being accepted. Almost 90% of the power is accepted by the antenna as long as the reflection coefficient is less than minus 10 dB. So we can then define the so-called bandwidth, the bandwidth of the antenna, saying that usable frequencies where the reflection coefficient is less than minus 10 dB. So in this case, it is somewhere between maybe this F1 and F2, the difference between them, somewhere around 2.4 gigahertz. Maybe this antenna can be used for Wi-Fi or Bluetooth applications where the frequency of operation is 2.4 gigahertz. So like what we saw in the Smith chart videos, this reflection coefficient, though only captures the magnitude of gamma A, if we want to somehow say even the phase, both the magnitude and the phase, of gamma, then the best way to view it is through the Smith chart, meaning we are plotting the gamma in the complex plane. So we see here that the gamma is plotted in this blue curve here as the frequency sweeps from a lower frequency to a higher frequency. We can see that the gamma is moving from the capacitive half of the Smith chart to the inductive half of the Smith chart. So which we can see here clearly from 1.8, maybe this is the 1.8 gigahertz, which is what we see here. As the frequencies increase from 1.8, somewhere the reactance is 0, which is 2.4 gigahertz. And beyond that is what you see here is maybe 3.2 gigahertz, where the reactance is positive, it becomes inductive, and the reactance is negative, the antenna is said to be capacitive. And right when the reactance is 0, that's when the antenna is at the resonant frequency, having just the real part. And here the Smith chart is normalized to 50 ohms. This point is 50 ohms. This is little higher than 50 ohms, which should match to the 77 ohms that we are looking at here. So this is just one example. So how to read from the Smith chart. So turns out that Smith chart, the 10 dB limits that you see in the frequency can be easily set by having a constant circle of a magnitude of reflection coefficient equal to 0.316, and minus the 10 log 10 of this gamma is going to be minus 10 dB, and that becomes the minus 10 dB circle. And where the antenna's impedance cuts through those 2 points here, that circle is essentially these 2 points here. So we would be able to find the so-called bandwidth of the antenna. So a Smith chart is the most complete descriptive details of all the real part and the imaginary part of the gamma, as well as the antenna impedance. Or alternatively, we can just look at the reflection coefficient or the impedance alone.